Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 3, 2026, about 6 days ago. It establishes a theoretical framework to explain entropy collapse during reinforcement fine-tuning, proposing a new control method that improved the QN 2.5 model's average score on the AI ME24 benchmark from roughly 17 to nearly 20. The paper is titled, On the Entropy Dynamics in Reinforcement Fine-Tuning of Large Language Models. And as we'll see later, the insights here offer a unified way to understand and improve how we train large models to balance exploration and exploitation. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 validates the theoretical link between the discriminator score, S*, and the direction of entropy change. In panel A, which focuses on positive samples, retaining tokens with a positive score causes the blue line to drop, signaling entropy collapse, whereas retaining negative scores pushes the orange line up. Panel B shows that for negative samples, this effect reverses completely. Finally, panels C and D demonstrate that masking these gradients allows us to manipulate the outcome, proving S* is a reliable control signal. Moving to the practical application, Figure 2 demonstrates how clip B and clip verses actually control entropy. Panels A and B track the clip fraction, meaning the percentage of tokens masked at each step. We see that adjusting the hyperparameter mu changes this fraction significantly. A lower mu, shown in orange, results in more aggressive clipping. Panels C and D then reveal the impact on entropy. While the blue baseline collapses, the clipping methods successfully maintain higher entropy, proving that stronger intervention effectively preserves exploration. So, now that we've seen how these methods stabilize entropy, Table 1 reveals the impact on actual performance. Here, the authors compare their clipping techniques against vanilla group relative policy optimization across 3 benchmarks, AIM24, AIM25, and DAPO 500. Looking at the QN 2.57b model section, we see a clear lift. On the AME24 dataset, adding batch normalized clipping improves the pass at K-score, which measures the diversity of correct solutions, from 50% to roughly 57%. Similar gains appear for the larger 14B model below, where vocabulary normalized clipping boosts the AIM25 average score significantly. These results confirm that preventing entropy collapse effectively preserves exploration, leading to stronger outcomes. Alright, Figure 3 validates the theoretical framework behind those performance gains. Here, we track the behavior of the discriminator score, S*, across training steps. The blue line represents the batch average value of S*, which starts high and gradually decreases. In contrast, the orange line at the bottom tracks how much S* deviates from its sampling expectation. Because this orange line stays effectively at 0, it confirms the mathematical proof that the deviation term vanishes, validating the core derivation. Well, Figure 6 details the full training dynamics for the QN 2.5 models. The top rows cover the 7B version, and the bottom rows the 14B. In the far right column, the orange baseline curves crash to 0, illustrating entropy collapse, while the blue lines for clip B and clip verses maintain healthy diversity. This stability pays off in the first 3 columns, where the proposed methods consistently achieve higher accuracy on benchmarks like AME24 compared to the baseline. So, moving beyond Q.5, Figure 7 tests whether these benefits hold for other architectures like QN3, distilled llama, and intern LM. In panel A, looking at QN3, we see the familiar pattern where the blue baseline suffers entropy collapse, while the clipping methods keep it elevated. However, the most dramatic result appears in panel D, on the far right, which tracks the gradient norm for intern LM. Here, the blue line explodes late in training, signaling a complete collapse, whereas the orange and green lines remain flat. This confirms that theoretically grounded entropy control effectively stabilizes training, even for models prone to failure. Wrapping up, 2 main takeaways stand out. This research replaces trial and error heuristics with a principled mathematical framework for understanding entropy dynamics. By simply clipping gradients based on the entropy discriminator, we can prevent model collapse and boost reasoning capabilities across diverse architectures. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.